Hello, it's Keith here, and this is lesson 1 of my SuperH assembly programming tutorials. What is the SuperH? Well, you probably know if you're looking at this video, but it's a processor that was used in a wide variety of the sort of late 90s era computers. And it's quite an interesting processor, and it's actually now being open sourced. The patents have expired, and there's an open source implementation of it. So I think it's one that's definitely worth looking at. Now we're going to be looking in these tutorials at the 32X and the Saturn, which both used to do various versions of the SuperH processor. It was also used in the Dreamcast and some various pocket PCs as well. So as I say, it's a processor you do see around, and I did actually see a SuperH4 processor in an old tape drive I was taking apart the other day. So it's definitely a processor that saw a lot of use. It's definitely an interesting processor. Now the processor is 32-bit and it has 16 general purpose registers. These are numbered R0 to R15. R15 is also the stack pointer though, so you probably don't want to use that one too much. It has some special purpose registers as well, which do other things, and we're going to see those as we go along in our tutorials. We're not going to discuss those at this early stage. Now, one important thing that we do need to discuss is branch delay slots. So the SuperH processor is one of these systems that has delay slots. This means that a command that comes immediately after a branch, like a goto command or a go-sub command in BASIC, the equivalents in assembly, which we will look at, the command immediately after will actually run before the jump or branch occurs. Now, why is that? Well, it's all to do with the way the processor works. These more modern processors, they actually are working several stages ahead in the reading and processing of commands. So by the time the processor realizes it needs to branch, it's actually started executing the following command. And so by running that command, even if we're going to branch, we actually gain a little bit of efficiency, although it does make the coding a little bit confusing. Now, what I would recommend for you as a beginner is what I've done in these tutorials is I've always put a no-op command, a NOP, it does nothing, after the branches, and that means that the code is very easy to read. It doesn't use that delay slot and it keeps the code working correctly. We're going to see this all in our code, but it is something that's very fundamental to the way that the processor works. Anyway, enough talk, let's go over it and let's see some code in action, because I know that's what people want to see. Okay, so what we're going to look at first is a minimal example. You can download all of the source codes and all the build scripts and the configured emulators from my website. So the intention is you can download this, you can run it yourself, and you can get started pretty much immediately with the scripts I've written. So if we press F6 here and we select an assembler, we can use ASW SuperH or ASW Saturn. Now this example script will actually compile on either. So we're running this minimal example here, and you can see it here running on the 32X, and here's the resulting example. But if we prefer, we can actually run it on the Saturn. We just select Saturn here and hit enter. And here is a Saturn emulator showing the same example. Well, how does this work? Well, it's very simple. Basically, you've got this header and this footer here, and they're including various ASM source files. The include file is attaching extra source code to the actual program, and so this program in the middle is the generic code, and the bits at the top and the bottom have various modules for the platform specific hardware to do the graphics work and things like that, so that the result is the same using these simple commands. So what commands have we got? Well, we've got a print string command, so we're showing a hello world message here. You can see the message down here. We've got a new line command here. We've got a monitor, and the monitor is actually showing the contents of the registers as a simple debugging tool and an educational tool in this case. We've got a memdump. We are dumping the contents of address in register R1 and the number of bytes in register R2, so you can see that we have dumped that area, and that's very handy for testing and figuring out what's going on. And then we've got a page flip command. This is for the 32X. We need to do a page flip to update the video display. And then finally we've got an infinite loop here, which is just a simple way of stopping the processor. An infinite loop goes on forever and never does anything. Now, all of these are various subroutines that I've written that are contained within the basic footer, essentially. Now, you will notice here that these all have the command BSR, and this is branch to subroutine. A subroutine is like a go sub in BASIC. So we're running all of these little subprograms that are doing some work for us and then returning. These all have delay slots, and as I say, this means that the command immediately after the BSR command will actually be executed before it, which sounds ridiculous, but that's the way the processor works. So all you need to know at this stage is whenever you use a BSR command, put a no-op command, NOP, afterwards. This is no operation, it does literally nothing, and that just fills up that delay slot and keeps everything running nice and simply. So you'll notice after each BSR we've got a no up, and the branch command is like a go-to. So that's not a subroutine, that's just a branch, a repeated loop, like a jump. And you'll notice we've also got a no up after that as well, because the branch also has a delay slot. And the way I've configured Notepad++ here is that the commands will appear in pink if they have a delay slot. So you'll see all of these are pink because they all have delay slots, and that's just to remind me to put a no up in there. Okay, you'll also see an align command that is keeping everything 32-bit aligned. You don't need to worry about that too much at this stage. But one important thing we do need to discuss is the concept of things like comments and labels and commands, because that is really fundamental. Comments, nice and simple. Anything starting with a semicolon, the rest of the line is a comment and will be ignored by the assembler. So these are just nice bits of information to help us out. Now, if our information is at the far left of a line, like this inf loop with a colon at the end, this means this is a label. Now this isn't something that's actually compiled into the final code. The assembler makes a note of the position in the code that's occurred and the equivalent memory address in the final program, and this is used later on in our program. For example, this branch here is saying branch to infinite loop here. Well, infinite loop has been defined up here by this label, so the assembler knows what memory address that is to branch to. You will notice that these commands, this branch command, this no up command, and all of these commands are tab indented. That is the difference between a label and a command. Now, if we don't put that tab in there, it's likely that our commands will be mistaken for labels and we will have a bad day. So make sure you tab or space indent your commands and you keep your labels at the far left and put a colon at the end. That will make everything nice and clear and make it work correctly. So there we go. So that's the simple example, and if you want to play around with commands on your own, I would suggest you start from this minimal example because it's got various little tools to help you out, and as I say, it assembles for both the 32X and the Saturn. Now, in these tutorials, the vast majority of the code will work on both systems. The lesson tutorials we'll be looking at. However, there are some cases where they don't. This is because in some cases the memory addresses work slightly differently, and if we're writing to fixed memory addresses, maybe they won't work quite as planned on some systems, but generally it will work on both. And hopefully, if you're following along at home and you're assembling and running on the systems I'm showing the examples, you should get the exact same results. Okay, so let's make a start with lesson 1. So lesson 1 is the absolute beginners. We're just going to cover some simple commands and we're going to learn how assembly works, and specifically with the SuperH. So what you want to do is we've got this jump block up here with various branches, and you need to rem all of them out except for one. So we're going to do the first one, example moves. Let's just fire this up, and let's fire it up on the Saturn for some reason. No reason particularly why. The Saturn is as good as the 32X, so we'll run it on the Saturn. Okay, so this branch here is going to jump to the label example moves, and you can see this down here. Okay, so let's fire this up and let's see what we've got. Okay, so what have we got here? Well, we've got a command here. You can see it's tab indented, so it's not a label like example moves. And this command is move. And then we've got a value with a hash at the start. And the hash at the start means that this is an immediate value. What does an immediate value mean? Well, this means that this is a value, a numeric value that is assembled into the command bytes themselves. You see, when the SuperH commands are assembled, these compile down, and certain data can be contained within the command itself, and other data that's too big has to be stored somewhere else, and a relative reference to that data has to be assembled into the command. So this move command here will compile to a single command, and this value 127 will be compiled within that command itself. Now, what does this command do? Well, you'll see we've got a comma here. Now, the value on the right is R0. That is the name of a register. So R0 is the destination, and the immediate value 127 is the source. And so what this is saying is move immediate value 127 into destination R0. And you can see that the source is on the left of the comma and the destination is on the right of the comma. So this is going to move the value 127 into register R0. And you can see down here we're running the command monitor 3, which will show 3 registers to the screen. And of course, you can see it's pink, which suggests that that has a delay slot. And so we've got a no up command after our BSR command there. So that's subroutine call. Now let's just quickly see what R0 contained. Well, R0 contained the value 7F. if you are new to assembly, you're probably thinking, why is it loaded with 7F rather than 127? Well, that's because these values are being shown in hexadecimal. And if I type in 127 here into my calculator, you will notice that the decimal value 127 is the hex value 7F. And we're showing all these values in hexadecimal because otherwise they wouldn't show very well on the screen. So that's why we're doing that. So here we've moved the value 127 into R0. Here we've loaded the value -1 into R1. Now -1, rather strangely, is again, if you are not familiar with assembly, if we just do a value of -1 here, you will see that the value -1 actually equals a lot of Fs, as many Fs as we can fit in our register, in fact. And so you can see that the -1 value in R1 becomes an awful lot of Fs there. So that's how a negative value is represented in hexadecimal. If you don't understand how negative hexadecimal numbers work, I completely understand. I didn't understand at the time, but now I do, and so I've made a tutorial on my YouTube channel. If you search, you will find I've got a whole video on hexadecimal numbers representation in assembly, so please take a look at that. You'll probably start to understand them as you go along, though, and I'm sure there's other great tutorials on them out there. If you don't want to use mine, that's absolutely fine. So the final command we've got here is we're loading the value -128 into R2 here. Okay, and you can see that that actually becomes this value here. Now, why have we loaded the values 127 and -128? Well, this is to make it a point. All of these commands compile, assemble to 16 bits. That means that the final data will be 16 bits worth of data, and so there's a fixed limit to how big the immediates can be because of that size. If we'd have tried to load in the value 128 here, this could not have assembled into a single command. And so the reason we're using these values is that the value 127 to -128 is the limit for a single byte. Now, in fact, the way the assembler works, we can actually put an immediate value of 128 in here and assemble, and it will work fine. However, the command actually assembles to something that doesn't actually use an immediate value. With this processor, the way that it works is that values that are too large for the actual command, the assembler will actually store these at an alternate location and store a reference relative to the current running line of code to that location. And we're going to see these in the following commands. So what we're doing here is we're loading some much larger values. These are far too big for a single byte, and the assembler is going to very kindly fix this for us. And how does it fix this for us? Well, what it does is it looks for an LT-org command. And if we search for LT-org, this command here will actually tell the assembler any values that are too big for immediates actually store at this literal org. That's what LT-org stands for. And store a relative reference, so an offset in bytes to that location, to actually get the final value for it. So if we store a 32-bit value, for example, and we want to load that into one of our registers, that 32-bit value would be stored at this LT-org, and the command would actually store a relative offset to that LT-org within the code. So if we run again here, you will see we're loading all of these various values here. We are loading a decimal value 1, 2, 3, 4, 5, 6, 7, 8 into R0 here. And if we just check this out, if we type in here 1, 2, 3, 4, 5, 6, 7, 8, and we bring up this calculator here, you can see that that is BC614E, and you can see that that value has been loaded in here. So that has definitely worked. You can also see that we've loaded that, so that's a decimal. That's the normal number system that we're all used to, having 10 fingers. We can also use binary, which is very popular in assembly and is certainly something you will use. We specify this by putting a % symbol, and that can only use ones and zeros. If you're not familiar with binary, you will need to learn it. And of course, we can use hexadecimal. We use a $ symbol with this assembler. It might, if you're using a different assembler, it might vary, but we use a $ symbol here, which is something I'm very familiar with. So we're loading the value 660, 660 here, and you can see that that value is very clearly there. So hexadecimal is very easy for us to use with these examples because it is very clearly represented. Now we can actually even use ASCII characters. So here we're loading ABCD into R3. We just put apostrophes around it, and you can see here if we get up our thing here and we type in and we use the correct case A, B, C, D, you can see this should be 41, 42, 43, 44, and you can see that has indeed been loaded there. So all of these values have been loaded in just correctly into our registers. So the assembler has done some work for us there, and let's actually take a peek at what the assembler has done. Now what we're looking at here is a listing file. Now this has been created by the assembler. The assembler script is this batch file here, and I'm using ASW in these tutorials, so if you're using my scripts you will be using this, and we are specifying to assemble the source file, we're specifying the processor, but we're also outputting a listing file, and this listing file is the actual source and the resulting code that is built by the assembler. And so you can see here that when we loaded in the value -1 into R1 here, that was the command we specified, we can see that the bytes that were loaded as a result were E1FF. Now FF is -1, so that immediate was actually assembled into the 16-bit command here. And 127 is 7F, and register R0, you can see that the 0 here is after the E, and 7F is indeed 127. And here we loaded R2 with -128. -128 is 80 as a single byte, and we loaded register 2, so you can see that's E2 there. So you can see that the register number is the second nibble, the second character there. The first character is always an E, and the value that we loaded in is the third and fourth characters there, the second byte of that 2-byte command there. So you can see that those commands are represented there. However, when we loaded this value here, well, this is a 32-bit value. This is 4 bytes, and that is far too big to load into that 16-bit command because it's a 32-bit value. So instead of using the E commands here, we've used the D commands. And so you can see that when we've loaded registers R0, R1 and R2, the commands are D0, D1 and D2. And these values here are actually relative offsets to that literal org. And so if I do a search for LT org here, well, you can see here that you've got that 660, 660 here, and you've got that 41, 42, 43, 44, which were the A, B, C, D. The assembler has moved all of these values here, and it's loaded a relative offset within the actual commands that it's assembled into the final program. So that is how the assembler has worked around the fact that we're asking it to do things that a single command literally can't do. Now, in our code, we're not going to worry too much about what is an immediate and what is actually being loaded at the LT org. The important thing to know is the LT org has to be relatively close to the current running code. If it's too far away, then you will get errors because the relative offset can't be loaded in the command. But the good thing is we can have multiple LT orgs in our program code. We just need to make sure we put them not in the middle of our code. We can't put an LT org here because these are running, the code would try and run the literal bytes within the sequence, so we would need to put them after our code branches somewhere else. So after this branch here we could put an LT org if we wished, and you can see we've got some test values there that we'll see in just a moment. So that's how immediates work. This is how the literal org works, and we've also learned how we can specify various different types of data we really want to work with. So that's how we can work with immediate data. How about if we want to move values between registers? Well, of course, that's a very important thing, and we can definitely do that. So what we are doing here is we are specifying a pair of registers here. So we've got the move command, the same command as we used up here, but this time we're specifying 2 registers. Now, as before, we've got a comma, and as before, the register on the left is the source, and the register on the right is the destination. So what we're doing here is we're moving from register R0 into R1, and from register R0 into R2. Now, despite being called move, it's actually a copy. R0 is left unchanged. So you can see here that R0 has been copied to R1 and R2 here. Now, we can actually use any of our registers, of course, not just these low numbers. So here we're moving R1 to R14. Now, I've not shown that to the screen, but as I say, I'm just making the point that any of our registers can be used. So any of these are available to us. We tend to only use the low ones just for simplicity because all of these commands work with any register. But of course, just bear in mind that R15 is the stack pointer. The stack pointer is very important to the functioning of the processor. We'll discuss it later on if you don't know what that means in a later lesson, but just for now, you're welcome to use the low numbered registers. Just leave R15 alone because it's got its own special things it needs to do. As I say, while we don't want to be loading to R15, we can load from it just fine. We can read it and we'll have no problems. It's just if we write random values to it, we will have a bad day. So here we are loading from R15 into R0. R15 can also be referred to as SP, short for stack pointer, and so we are loading that into R1 here, and you can see that we have loaded these values in here. Those are the values loaded in from the stack pointer. The stack pointer is used by the subroutine, the processor, during the execution of subroutines and various other things, so we do need to leave it well alone. Now, in all of these cases, we've been basically using immediate values, the LT-org, and then the values of registers, but there will be times we want to do other things and load in from memory addresses. Now, what we're going to do here is we're going to specify some data in our code here, and we're going to give these a label. So we're defining a label called test value, and we've put that value there, and test value 2, and we've put that value there. And what we want to do is we want to load the data from these addresses. Now, the way that this processor works, what we want to do actually first is we want to load the address into one of our registers. Now, we can specify these as an immediate, so all we need to do here is move the address of test value, the label, into R5, and the address of test value 2 into R4 here. That's what these commands are doing. And then we can use those addresses in those registers as the source, and we use the @ symbol to do this. So what this is saying is move from the address in R5 into R0. So it's not the value in R5 that's being used, it's the value at the address in R5, and that's why you could think of, that's why we've got that @ symbol. It means at the address in R5. So again, the source is on the left, the address in R5, and the destination is on the right, the actual register R0. So you can see here we're loading from the address in R5 to R0, the address in R5 to R1, and the address in R4 to R2 here. But there's a catch. Now, in the past, you'll see we've been just specifying these move commands, and we've not really been specifying anything else. But you may have noticed we've started specifying something after that move command. We've got a .l, and in fact, we've got a .w and a .b here. What do these mean? Well, in the past, these commands have all basically worked in 32 bits. We've specified full 32 bits here. And when we specified a signed immediate here, it was being extended to 32 bits. So even though the value was a byte, it was filling the entire register. However, now we may not want to load the entire 32 bits. Maybe the source data we've got isn't 32 bits in size. And so we can actually specify the length that we want to load. Now here we've specified that we're moving a long. Long means 32 bits. So we're moving a long 32-bit value, the immediate value test value, into R5 and R4. We're then specifying here we're loading a long. Here we're loading a word, and on this processor a word is 16 bits. And then we're specifying a byte, and a byte is just 8 bits. So there we go. So these are saying move a long 32-bit value from the address in R5 to R0. This is moving a 16-bit value from the address in R5 to R1. And this is moving an 8-bit value from R4 into R2. Well, we've got these test value and this test value too, so let's just check these out. So here they are. And you can see here that that is what has happened. So we've loaded the full 32 bits into R0 here, and then we've loaded a 16-bit value into R1 here. Now you can see FEDC here, and that has been sign extended and to fill all the remaining bits. What does sign extended mean? Well, this means that any extra bits that we didn't specifically load, so the remaining top 16 bits, are filled with the top bit of the amount that we did load. So the top bit of the 16-bit value was 1. The F has a top bit of 1. So the remaining bits are all filled with that 1, and they all become Fs as well. Now the byte value that we loaded here, we've just loaded the value 1, 2 here. Now that it has a top bit of 0, the nibble 1, the top bit is 0, and so all of the remaining bits are filled with zeros here, so that has been 0, sign extended with 0 here. So that byte has been loaded in and sign extended there. Now this is where something quite important to this processor comes in, and all processors. How is data actually represented in memory? Now there's two kinds of concepts. There's the concept of big endian, and there is the concept of little endian. Now these basically refer to the order that the bytes are stored in. Little endian would effectively store the bytes in reverse order, but big endian stores them in consecutive order. So basically the most significant byte, the 1, 2 byte here in this 32-bit value, is the highest value part of the value of 1, 2, 3, 4, 5, 6, 7, 8, and so that is stored first in memory at test value 2. And so when we loaded in a single byte from test value 2 here, we got the top part, the 1, 2 part. On a little endian processor, we would have actually got the 7, 8 part. Now, on these systems, the SuperH is running in big endian mode, but in theory, the processor can run in big endian mode or little endian mode. So if you're doing something on a different system, you just do need to bear that in mind. For today's purposes, the processor is big endian, but depending on what you're doing, it might not be. So that is something to note. Now, here we've specified long, word and byte here, but we did do one final command. We used a move command without specifying any size. So we've moved from R5 into R3. And you can see here that R3 has loaded a full 32-bit value. Now, in virtually all of the cases, these commands will work in long mode if we don't specify the length. The only exception is commands that literally don't operate as the long. Some commands only work in 16 bits, and so those would not work in 32 bits, obviously, if we didn't specify. But you know, I'd suggest, at least as starting out, it might be worth just always specifying long anyway, just for clarity, just so you are clear. But as I say, if you don't specify anything, these commands will always work in 32 bits anyway, and commands like this, working in between registers, will always copy the full register anyway. So there we go. So that's how we can specify to use the address in a register by specifying an @ symbol. But we do have even more options. So we have the option of post increment. So what this means is that here we're going to load a byte from the address in R4, but after we've loaded that byte, we're actually going to increment R4 by the 1 byte that was loaded. So R4's value will change by 1. The address that we loaded from will move across by 1 in memory, and so each time we run this command, even though we're running the same command over and over again, we're actually getting consecutive bytes. So we got 1, 2, 3, 4, 5, 6, 7, 8 in memory here. We've done these commands over and over again, loading a byte each, and we get 1, 2, 3, 4, 5, 6, 7, 8 here. And the value in R4 has actually gone up by 1 each time, as we've loaded 1 byte each time. Now, we're going to go into these kind of commands in these addressing modes in much greater depth next time. I have a whole lesson on addressing modes, so we're not going to cover that anymore at this stage. I just wanted to show you that the addressing modes had more advanced options than just loading from the fixed address there. We'll go into that more next time. Now, we've looked at various ways to load values there, but now let's take a look at actually using some values. So what we're going to do now is we're going to do some addition and subtraction, some mathematics. Okay, so what we're going to do is we're going to load some immediate values into R0, R1 and R2 here. We're going to show those to the screen. And then we're going to do some commands between registers here. So what we're going to do first is we are going to do an add command, and we're going to add R2 to R0. So this is effectively saying R0 equals R0 plus R2. Again, the source is on the left, the destination register is on the right, and R2 is unchanged by this, so it's only the destination that's changed. So that's what we're doing to R0. We're then going to subtract R2 from R1. So this is like saying R1 equals R1 minus R2. That's a typo, I do apologize. So R1 equals R1 minus R2, that should be. So that is what's going to happen there. So at the start, R0 was equal to 2, and R1 was equal to 2, and R2 was equal to 1. R2 has been unchanged, but the addition has increased R0 to 3 and decreased R1 to just 1. And you can see that as a result of those. And then we've done the same again. And of course, R0 has become 4, and R1 has become 0 there. So that is using a register as the parameter for an addition and a subtraction there. Now that is using a register as the parameter, but we can also use an immediate. So here we're using the immediate value 1. You can see that hash symbol specifying an immediate. And so we're adding 1 to R0 here. And we don't have a subtract command, but we can add a negative value, which basically the same thing. So we're adding negative 1 to R1 here, effectively subtracting it. So you can see R0 after adding 1 became 5 here. And R1, which contained the value 0, went negative, and this ends up with a value of all f's, which is effectively -1. Now, why is that -1? Well, basically, if we added that value to what the value 1 in a register, it would effectively cause that register to go down by 1 because of the way processors work and negative numbers in assembly and hexadecimal work. I can say, if you don't understand it, I fully understand, but you do need to look into that and find a tutorial either from my website or somewhere else to explain how negative numbers work in assembly, because you will need to have a reasonable understanding of at least the fact that they do work. So there's some simple mathematics, just so we've done more than just moving values around, just so we can show that you can use them as well. The final thing we're going to do is just have a quick look at calls and jumps. And the reason for this is we have to use calls and jumps. We're using them all over the place to run these little test programs. So let's take a look at them now. The important thing is, of course, as I say, we've got these delay slots, and that means we always want to put a no up command after our calls and our jumps here. But so what are we doing here? Well, here we are branching to BSR is branched to subroutine. We are branching to the subroutine show hello, and you can see we've got this subroutine show hello here, and it's showing it's running more subroutines, this print char routine, and this is a piece of code I've written, and it shows the value in R0. So we're showing hello by loading consecutive values as immediates into R0, and we are running this print char routine repeatedly. Now you will see I've been a little bit tricky with this last one. All of these have got a no up in the delay slot, however the last one does not. We've loaded the letter 0 into R0 after the final print char routine, but as I say, because of the way the processor works, that is actually executed before the print char routine. So you can see the last print char shows the letter O. So that is how the delay slot works. Now, you'll see that we've got these commands here. What are these? Well, again, I didn't really want to explain this at this stage, but we have to because we just can't run these commands otherwise. Now, when we run a subroutine, the return address is loaded into a register known as the procedure register. This is a special register, and this is effectively the return address. The problem is that when we run a subroutine, the procedure register is actually changed, and so this command here will effectively break the procedure register because it no longer contains the correct value for when this subroutine is finished. So we need to back up that procedure register using this store special register, and we're storing it onto the stack here. That's what that command means. Don't worry about it for now, we will cover it again later. And this command is basically restoring the procedure register at the end of our subroutine. The final command in our subroutine is a return from subroutine RTS. That also has a delay slot, that's why I've coloured it pink. And so again, we have a no up after that. So this subroutine is self-contained. We can nest subroutines in here because we are backing up our procedure register here. And that's what we're doing there. And we're running that subroutine with this branch to subroutine here. So we're doing a subroutine there, we're doing a subroutine here. We've got a subroutine here as well. Again, in all of these cases, we are using the delay slots. Now, you can see here, we've loaded the value A in here. But if we unrun this example code here, now this is now in the delay slot here for this print char. And so the value A will never actually be shown here because this command here was executed before the branch. So you can see that the A has been replaced with a question mark because of that change there. Again, as I say, you've got to be careful with your delay slots, and they will probably catch you out, I'm afraid. As I say, I've made everything pink here just to highlight these commands that have delay slots, but it's an easy mistake to make. Now, all of these BSRs are branches to subroutines, but BSR does have a limit as to how far within our assembled program it can actually jump. If the destination is too far away, that command won't work. And at that point, the alternative is the JSR command, which can jump to any destination. However, the destination has to be loaded into a register. So here we are jumping to the print char routine via the JSR command, but we have to load the address of print char into R13 and then jump to the address in R13 with that @ symbol specifying that the address in R13 is the parameter for this command, this JSR command. So that's how we can jump to a subroutine that's a very long distance away. We may not want to execute subroutines. We may want to actually skip over bits of code. Now we can do that with branches like a goto or a jump, So this has no return. It does not alter that procedure register, so the PR register is unchanged by this. So here we're branching to the label skip C. You can see the label skip C here, and that effectively doesn't show C to the screen, because this code would show C to the screen, but we've skipped over it permanently. So you can see we show A, B, D, F with no C because we skipped over it. Now here we're using a branch. Again, that is a command with a limited destination. It's got to be close. If we want to branch to a very far place away, instead of the BRA command, we use the JMP command, and again the destination needs to be loaded into a register. So this is again like a go to or a jump with no return. So here we are jumping to the label skip E, so we don't show the E to the screen. There are no E's here. So again, as I say, we've got all of these commands here. The final ones are ones I don't think you're ever going to need. These are branch to subroutine far and branch far. Now what do these mean? Well, these are relative code, but they are able to use a much larger range because again they are using a register as the parameter, but these are compiled relative to the current program code, so we have to calculate the destination as an offset from the current code position. And you can see I've got this star here. This star isn't a multiply star. This is actually telling the assembler that I want to use the current byte of code as the parameter here. The star is effectively the program counter, the running line of code. And I've had to use 6 here because the processor is actually always running a few lines ahead. The program counter is always the current instruction plus 4. And this move command is 1 line before the branch, so I need to specify plus 6 here to calculate the correct offset. Now why would you want to do this? Well, this is for something known as relocatable code. Maybe you want to load your code into one position in memory and then shift it to another and run it in that alternate position. You're probably thinking, why on earth would I want to do that? And at this stage you definitely don't. I'm just explaining these for completeness. Just so I can say I have. We've covered now all of the branches and jumps, but these are something you might need if you get very advanced. At this beginning stage though, as a rule, use branch and BSR. If you get an error saying that the destination is too far away, you may have to use JSR and JMP, and in those cases you will just need to load the address of the destination label into another register, as I have with register 13 here, and then the code will execute the same. These just keep in the back of your head because one day you might need them, but not today. So there we go. We've covered an awful lot today. Hopefully you have found it interesting. If you liked what you've seen, please like and subscribe. Please also go to my website. You can download my cheat sheet. I have a cheat sheet, which is a free document that has a wide variety of... it has all of the instructions of the SuperH and a wide variety of information on them, including the compiled bytecode. You can see it's far too small on this screen, but you can print it out at A4, or if you're feeling adventurous, even A3, and you can use it at your leisure, and hopefully you will find it very educational. If you are interested and you want to support my content and get some printed material, I do have some books available. I have 2. They don't cover SuperH yet. I'm planning to do a SuperH book in the future. But the first book covered Z86, 502, 628,000, 8086 and ARM. The second one covered ARM, Thumb, 65816, 6809, PDP-11 and RISC-V. They are both available now, so please take a look at those if you want some printed material on assembly. And I do cover all of those processes in other tutorials on my YouTube channel and website, so check those out. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.